Hi, my name is Alexander Knopp, and this is Introduction to Combinatorial Game Theory. In the previous video, we defined the Sprague-Grundy function, and we proved that if a position has the value 0 of the Sprague-Grundy function, then it's a p-position, and vice versa. If it's a p-position, then it has the value equal to 0. However, one may ask a question, why do we need the Sprague-Grundy function? Because if it's just a proxy for finding p and n position, then it's not that useful. However, in this video, we're going to show that for a big class of games, it's way easier to compute the Grundy function than to find p and n positions directly. We start with an example of such a game. Assume two players have two piles of chips. They take turns to make a move. And on each turn, the current player removes one or two chips from one pile. The one that cannot make a move loses. So this game is very similar to the game of Nimbad. In this game, you can remove only one or two chips instead of any number like in the game of Nim. And this similarity would allow us to bring the ideas from the game of Nim to this game. The key observation here is essentially that these two players are playing two games simultaneously. And on every turn, they can decide in which game they want to make a move. And if they cannot make a move in both of them, they lose. So this leads us to the following definition. So let G1 and G2 be two graphs then G1 plus G2 is also a graph, so that the set of vertices of this graph is the Cartesian product of V1 and V2, and the neighboring function is defined as follows. N of x1, x2 consists of two sets. First, it's where you can make a move in the first game, so it's y1, x2, such that y1 belongs to n of x1. Union, the second part, where you can make a move in the second part. So x1, y2, such that y2 belongs to n of x2. It's easy to see that this game is a sum of G and G, where G is a game where the set of vertices is equal to the set of non-negative integers, and the neighboring function is defined as follows. N of x is equal to either x minus 1 and x minus 2 if x is greater or equal than 2. It's the set consisting of x minus 1 if x is equal to 1, and it's an empty set if x is equal to the empty set. And the final ingredient for analyzing this game is the theorem that allows us to compute the Grundy function for a sum of two games. So let G1 and G2 be two graphs, and G1 and G2 be the Sprague-Grundy functions for them respectively. Then g of x, y, that is equal to the nim sum of g of x, g1 of x and g2 of y, is the Sprague-Grundy function for the sum. Using the discussed theorem, we can finally study this game. So in order to do this, we need to compute the Grundy function for this game when you have only one pile. So let's start with a table of values so that we could guess the pattern. So you have either 0, 1, or 2, or 3, or 4, or 5, or 6 chips. And the Grundy function for 0 is 0, just because it's a terminal position. From 1, you can go to 0, so the max of 0 is 1. From 2, you can go to 1 and 0, so it's a max of 0 and 1, so it's 2. From 3, you can go to 1 and 2, and it's a max of 1 and 2, so it's 0. From 4, you can go 3 and 2, so their max is 1. Similarly, from 5, you can go to 3 and 4, so their max is 2. From 6, you can go to 4 and 5, and the max is 0. So now we can conjecture that the Sprague-Grundy function for the one-pile version of the game is g, such that g of x is equal to either 0 or 1 or 2 if x is divisible by 3. So for 0, 3, 6, and so on. If x minus 1 is divisible by 3, we have 1, because it's 1 for 4 and for 7 and so on. And finally, it's 2 otherwise. And using the theorem, we know that g of x, y, the Sprague-Grundy function, for the game is g prime of xy, so that it's equal to g of x XOR g of y. In other words, g prime of xy is equal to 0 if x and y are divisible by 3. It's 1 if x is divisible, and y minus 1 is divisible by 3. Just because this is XOR of 0 and 1. Similarly, you have 2 if x and y minus 2 are divisible by 3. And it's equal to 1 if x minus 1, y are divisible by 3. Just because in this case, for x minus 1, for x, the Grundy function is 1 because of this rule. And for y, it's equal to 0 because of this rule. So it's the nim sum of 0 and 1, which gives you 1. And if x minus 1 and y minus 1 are divisible by 3, this is 0, just because it's a nim sum of 1 and 1. And if x minus 1 and y minus 2 are divisible by 3, then it's equal to 3, because it's a nim sum of 1 and 2, which is 3, and so on. Therefore, we can, for example, conclude that the position in this game is a p-position when g prime is 0. In other words, it's when the remainders of division by 3 of x and y are equal to each other. In this video, we learned how to use the Grundy function to analyze a new class of combinatorial games, which is called the sum of combinatorial games. In the next video, we are going to learn how to apply this result to a class of games that don't look like a sum. However, it's still possible to use these ideas there. If you have any questions, ask them in the comments. See you later.